Hi, everyone. First of all, I know that I am the one between you and lunch, so I will promise I will try to make that talk fun and also interesting. Few words about myself. So my name is Nico. I'm a freelance front-end developer from Switzerland. It's my first time at Build Stuff and also my first time in Lithuania, and I'm having a great time with so many great people and great speakers, great talks. It's pretty amazing. I'm also part of the Google Developer Experts program for web technologies, and that means I spend a huge part of my free time just playing around with all kinds of new browser APIs, web APIs, technologies, and everything that's new in Chromium browsers. And I also like to talk about those subjects. Most of those talks I've given in the last 2-3 years were in English, some in German, and only 2 talks in Swiss German or in Berndeutsch, which is our local Swiss German dialect. And in September 2021, I had my very first talk in Swiss German at a local JavaScript meetup. And luckily that was recorded, so I'm able to show you some clips of that talk.
Im Endeffekt, schlussendlich, im Endeffekt, schlussendlich, wird im Endeffekt, aber im Endeffekt, schlussendlich,
That's no joke. That was a 30 minutes talk. And I was able to use the word schlussendlich and im Endeffekt over 35 times. And both words basically mean the same. It's finally or in the end. And I watched the video afterwards and I was just extremely annoyed. And last February, I had my second talk in Swiss German at the same meetup. And I was looking for ways to detect those words in my speaking. Luckily, there are browser APIs. There's, for example, the speech-to-text API that allows you to transform spoken words into text, and that actually works quite well in English and also in German, but not in Swiss German. So I had to look further, and in the end, or let's say those APIs, they are basically just running machine learning models. And can't we run them directly in the browser? Yes, we can.
im Endeffekt, schlussendlich.
Sorry. There we go. So in the next 30 to 40 minutes, I try to give you a short introduction into machine learning in the browser. And I really hope that some of you might be inspired to try their own models or create their own models on the device in the browser with machine learning. But let's start from the very beginning, because I'm not talking about any generative AI. We have seen a lot of great talks about OpenAI, ChatGPT, all of that stuff. But when I created most of my examples, I haven't even heard of ChatGPT. So I would like to focus on the core concept of artificial intelligence, which is machine learning. Let's have a look at this very simple example. We have a car, and we want to add some self-driving capability to that car. So we have a sensor. Whenever the sensor reaches a certain threshold, we will just turn 180 degrees and we have our self-driving car. But it's not very intelligent, right? Let's add more sensors. We have 2 sensors. So now we are actually able to see whether the object is on the right side or on the left side, and we can then react accordingly. And our code on the left-hand side is a little bit more complex, but I mean, it's fine. Problem here is that we have 2 sensors, so we are not really able to identify objects in front of us. Let's add more sensors. So when Tesla had their first Model S, they had around 8 infrared sensors in the front of the car before they moved to a completely image-based recognition. And with those 8 or 6 sensors, we are able to detect objects quite well in front of us. But that's just the front. And as you can see there on the left-hand side, it gets complex quite quickly. And we are not talking about weather data. We are not talking about a predefined route. We are not talking about road signals. That's just the sensors in front of us. And there's no way to write an algorithm in a classical way. So we need something more. We need something like this magic prediction black box, where you can just put in all the sensor data, and it will then predict whether we need to turn, whether we need to adjust speed, whatever we have to do. And then that's actually what machine learning do for us. So instead of writing algorithm our own in the classical way, where we have if statements, while loops, and all sorts of that, machine learning is a completely different approach, where we have a set of predefined data and the expected output, and now we let the machine find the algorithm itself. We try to feed in the data, try to train the algorithm, and then we want to have the output for similar data to our input data or our new data as well. There are three main types of how we can train such algorithms. We have the supervised learning, which means we have labeled input data. We have, for example, 500 apples and 500 oranges. And now we gave all of those fruits a label, orange or apple, and now the machine finds a way to identify whether that is an apple or an orange. Then you have unsupervised learning. That means that we don't want to do all the work before to label the data. So we'll just have 1,000 fruits, and we will find, or we will let the algorithm find patterns itself. That means we can have some unexpected output, but it's also easier to get data. And there's reinforcement learning. That means, for example, we have a robot, and that robot tries to learn. There we can add rewards and punishments, and now the robot tries to achieve a certain thing with a reward. So that could be like when he reaches a certain distance, that would be a reward, and punishments when it falls down. So it tries to avoid punishments, get rewards. And that can also lead to some unexpected output. So for example, our robot learns how to walk with the hand to balance it out. And then we can add more punishments. So a hand movement would be a punishment, and then the machine trains a different algorithm to avoid those punishments as well. But let's talk about the elephant in the room. What is happening inside that magic prediction black box? We know it has something to do with machine learning, but what is it? We are talking about the artificial neural network. Let's imagine we have this 16 by 16 pixel canvas with hand-drawn numbers between 0 and 9, and we want to predict whether it is a 1, 2, 3, and so on and so forth. First thing we need to remember is machine learning models, they don't actually work with images. What they need is numerical input, and they also provide numerical output back. But we can convert any image into numerical input. And here we only have grayscale, so it's quite easy to convert that into a numerical representation. And we can then have this one line of numbers where we have 256 numbers that represent our hand-drawn 2. Now, the network itself looks a little bit like that, and that is a very, very oversimplified design. So if you are a machine learning expert or a data scientist, I know that it's oversimplified to a point that you could also say it's false, but it helps to make a couple of points. So first of all, we have our input layer. Those are those 256 numbers. And we have an output layer. And that output layers can be all the labels that we trained our algorithm for. So we have 0, 1, 2, until 9. So we have those output layers. In between that, we have hidden layers. And those are layers that consist of so-called neurons. Now, the value of a neuron is now the sum of all the neurons from the previous layer times their weight. And that goes through the whole neural network. So that means we have calculations, 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 calculations until we have our output. And as you can see now, we are 84% sure it's a 1. And we are 85% sure it's a 6. Our model has no idea what that number is. And that's because it's not yet trained. When we train a model, again, we have the labeled input. So we know that it should be a 2, and we have hundreds of examples where we know it should be a 1. And now when we train the model, it goes backwards through the model, and it will adjust the weight until we have close to 1 for the 2 and close to 0 for all the other labels. We train that, and we are now 89% sure it's a 2. The thing I want to showcase now is we have a very small image and only grayscale, so no RGB data whatsoever, and we only have 5 neurons in the first layer, but we already have 1,280 initial calculations to do. So we have a lot of calculations to do, and that's also why we try to use GPUs for machine learning models instead of CPUs, because it's just way faster and better at doing those calculations than this. So how can we use machine learning in the browser? There is a tool called TensorFlow. So in 2015, Google released TensorFlow, which is an open source machine learning framework, originally written in Python, but we now have a couple of different implementations. And since 2019, we also have TensorFlow.js, which allow us to use machine learning models right in the browser using TensorFlow. One good thing about TensorFlow is that all those complex the mathematical operations are not complex, but they're just a lot to do. And those operations, they are outsourced into so-called TensorFlow backend. There's, for example, the CPU backend, which was the first backend, and there all those calculations are happening in JavaScript on the CPU, which works, but is quite slow. We also have the WASM backend, where we have WebAssembly that does all those calculations. But the thing you want to use is the GPU, right? How can we access the GPU on the web? There is, for example, WebGL. And WebGL is basically a graphical layer on top of the GPU. So it uses the GPU under the hood, but is like this graphical layer on top. It's faster than WASM and way faster than CPU backend, but it's not optimal. The thing you want to use is the GPU directly. And since Chrome 113, which launched in last spring somewhere, we have the WebGPU API, and that means we can also use a WebGPU backend, and all those calculations are now happening directly on the GPU of our device. And that is way faster. It's up to 2 times as fast as the WebGL backend, but it also, it always depends on the device and also the model, but in general, it's up to 2 times as fast as WebGL. So let's have a look at some of the examples. Let's start the fun part of the talk. So first of all, we have an image, it's me, and we want to detect some key points and some faces in that. So what we can do is we can use TensorFlow, we can import TensorFlow, we can import the model. By the way, my slides will be online after the talk, so all the links from all the examples will be available right after the talk. But what you can do is you can now create a detector, and that detector now accepts basically any kind of data. So in that case, I will just add the image element, but I can also add a video element or an image bitmap. It basically doesn't matter, and it will then do the predictions of how many faces are in that image and also where are the key points inside those faces. If you go one slide further, we see that we have the image. I will now create a canvas element on top of my image. I will then draw the image into the canvas. I will take the image data from the canvas. I will then predict the faces of that canvas of the data. And what I can now do is I have the key points from TensorFlow, and I can now draw all the key points to the canvas, so I can predict all the movement that I have in my face. So I also created some examples, of course. So what we have here is the same technology in the end, but I'm using the video input, and that means as soon as the video starts, it creates a detector for that, and it will do the predictions as you've seen before. Once it's done, it will start the next prediction. Once that is done, it starts the next prediction, and so on and so forth. So we are able to identify the faces in the video, and as you can see, that's quite slow, and I'm using the CPU backend here. But I can also switch to the WebGL backend, and we are now already at 10 to 12 frames per second, which is way faster. And we also can use the WebGPU backend, and we are up to 20 frames per second. And that's already quite fast, so it's actually real-time face prediction in the browser. And I did that on May the 4th. So for some of you might know that this is the International Star Wars Day. So I did that to draw masks on top of my face. So what I did here is I took 2 key points on the outside of my eyes to determine the position of the image and also the size of the image. And I would then just like place the image on top, like place the PNG on top of my head. That's a very basic example. There's a very cooler example that also using TensorFlow and the browser, and that predicts the key points not only in my face but also in the example image, and it will then draw the image in respect to the key points that you have seen that is on my face. So we can now, for example, take Yoda, and it actually uses my my facial expression to draw the image on the face. Again, that is using WebGL, and it's happening quite fast directly in the browser. So having those landmark detections is fun, but it could be more useful if you would have things like emotion prediction. And that's possible as well, because we have our machine learning model. It returns this list of key points. So we have a list of numbers. We want to know whether it's neutral, happy, sad, angry, cheer. So we have a list of labeled output. That should look similar to you. So we have a list of input, numbered input. We have a list of, or a list of labeled output. So we can just add another machine learning model. And we can chain machine learning model based on what we want to achieve. So there's another library called Face API.js that uses TensorFlow under the hood. And the real problem I had is that my my own website uses a WordPress backend. So I have just a WordPress backend to feed some of the data, and I just don't want to have angry people in my WordPress backend. So I created this little bouncer. As you can see, I can't log in because there we go, it's disabled. So what I have to do is I need to smile. And now my little brown bear there decides that now it's the time to log in. Pretty useful. It's about fun, so it's fine to have those examples. So, but another example that I'm really, really happy with is I wanted to use machine learning on my own website. So the idea was to create this little JavaScript package that would use TensorFlow, would use the camera input, and would be able, or would enable me to control my own website using just hand gestures. I did it and it worked. The thing is, why should I do that only for my own website when we have, for example, Chrome extensions? And Chrome extensions, they are basically just injecting JavaScript on any site that you want to use. So I did some refactoring, and I now have this in, there we go, as a Chrome extension. I can go to my website, but it could be any website, because I have it as a Chrome extension that I can start. It uses the camera input. And now you can see the cursor, which is like the point between my index finger and my thumb, and I can use my my hand to navigate through the site. Up. There we go. I can just go through my site, through any site, just using hand gestures. And the way it works is, as you can see here, it takes the whole camera input. It predicts the 2 points on the tip of my index finger and the tip of my thumb, and it will then take the size of that to decide whether I have an open gesture or a pitch gesture, and that will then trigger different events on my site. And one thing you might notice is that the center of the circle is not in the middle between those fingers, and that is I did that on purpose because I realized that when I do the pinch gesture, my index finger moves way faster than my thumb. So I have the center of the ring, which is the center of the cursor as well, then closer to my thumb than to the index finger. And it does work. So having those video examples is all fun, but the thing I wanted to achieve is I wanted to to detect those words in my speaking, right? And words are not images, except when they are, because all the any audio sample that you have can be converted to a spectrogram. And when we have, let's say, 2 seconds of me talking or me saying a word, I can create this one model that detects those 2 seconds. And when I compare those 2 seconds to my whole talk, I can actually use that to detect those words in my whole talk. So let's have an example of a whole talk as a spectrogram, and I can now compare those 2 seconds with my model. One thing I had to learn is that normally words don't start after 2 or a specific amount of seconds. So I also had to add an overlay. That means that I have more predictions to do per second in my case. That would be an overlay of 0.5. And for my example, I even had to do an overlay of 0.95. So I have a lot of predictions from a lot of different areas of my talk to actually cut out the words that I was looking for. How do we do that in TensorFlow? So we have a speech commands model, can import the model, we can create the recognizer, we can then start to listen, and we'll take the audio input of our device and start prediction. It will just, with the overlap factor that I defined, it will just find those words while I am talking. The problem is that by default, the speech command models has some words like 0, 1, 2, 3, down, left, right, blah, 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 blah. So it has some predefined words, but of course, my words were not in that list because, well, they are garbage, would have thought. So I had to create my own model. And that's actually also doable just in the browser because there's a tool called Teachable Machine. I need to switch to a different browser. I have the project open, and what you can see here is I think it's 1 hour of me just reading a book as a background noise class. And then I have 50 samples of me saying schlussendlich, and I have 70 samples of me saying im Endeffekt. And what it can do is you basically just put in the example data, you click train, everything will happening in the browser. It takes about 10 to 20 minutes, so it takes some time, but it's not bad to have that trained on your machine right in the browser. I did that before the talk already because I don't have time to do that. But when I now start listening, I can say, for example, im Endeffekt, and it will trigger a spike on the im Endeffekt class instead of the background noise. So this actually works, and you're also able to import those newly generated models directly to the speech command model. So you have the model.json and the metadata.json, which are two files that are created by Teachable Machine, and I can now use those that model for my speech recognition program. Since my slides are running in the browser, why can't we add that to my slides as well? I mean, I did that. So I have now the keyword recognition, which is running in my on my slides, and as you can see there, it's now the background noise is the first class, so it's recognizing me talking in the background class. But as soon as I say im Endeffekt, it will trigger the buzzer. And I actually used that in my second talk in Bandage, and it was quite fun. I mean, I didn't use those words as often as before, but it did work out, and it really reminded me on not using those words. So why should we use machine learning in the browser? Well, first of all, it's very convenient to just send the URL. We have no drivers to install. We can just send the URL. People are already able to use it. It's interactive. Even though predictions would be faster on some very powerful server backend, we still have this the HTTP request, and there's no way that we can have a fluent video like face prediction in a live video just by using some server backend. Even though it would be faster there, we still have the network request. We can also combine the machine learning models with all the other web APIs that we have. For example, I had one talk where I am using Web Bluetooth, and I have a little Bluetooth car, and I was able to use the hand gestures of that, the hand gestures using TensorFlow that would then be translated to commands that would then be sent to my car using Web Bluetooth. So the web has so many great APIs. And also I have a talk in the afternoon in the beta room about a couple of other APIs where I have more examples with all those exciting features that we can use in the browser. But we can combine all those APIs with this one platform called the browser. And most importantly, all the data stays on the client. If we have image data, we don't want to justify ourselves why we are sending those to any server. It's just very convenient to just only have the data, the image data, the raw data on the client where we can do the predictions. And if we have to, we can then send the predictions to the server. But the raw data, the image data, the data that the user cares about will stay on the client. There are a couple of pretty great resources. Those are mainly projects by Jason Mayes. He is the Chrome DevRel lead TensorFlow DevRel lead at Google. And he talks a lot with founders in the TensorFlow space, where he has some great examples of people using TensorFlow to actually create applications that people use. And there's also quite a nice blog post by the Adobe Photoshop team, because there is a web version of Photoshop that is using some TensorFlow models. So they had some problems porting the TensorFlow.js models into their WASM stuff that they are doing in on the Photoshop web version. It's a pretty interesting blog post. Now, to end that talk, I would like to dive into some problems that can come with machine learning. So first of all, a lot of the AI models, they tend to be, or if you don't take care of that, they can be racist or sexist. And that's not because the developer wants them to be that. It's just because they are trained on data that maybe they're using historical data, or they're using data that we have right now. And our world is still in some cases racist and sexist. So we have to take care that we don't have biased data in our data set. And the second thing, even if you try to have no bias in our data set, there is one headline from The Guardian. It was in 2017, and it was an actual study from the Stanford University. So it's a pretty good, well-known university that created this machine learning model, and they claimed that they would be able to guess whether you're straight or gay just from a photograph. The headline alone should be very concerning, and of course, a lot of machine learning engineers jumped on that and tried to recreate that study, and they actually managed to do that as well. And the thing here is they took just images, profile images from social media, where they knew whether a person is straight or gay, and they were able to create this model that would then predict whether you're straight or gay based on your profile image. And while the model is correct, the problem here is their conclusion was completely false. And luckily, some engineers from Google, they looked into that issue and they tried to reverse engineer the model, and all that stuff they were able to just all of that fuss that just comes down to a fact that they were looking for cultural things in those images and not biological facts. So the problem here was they were looking for correlations, because machine learning models are looking for correlations and not causation. So the thing is, even if there are cultural traits that would make it possible to predict profile pictures or predict the sexual orientation based on profile pictures, it is false to claim that it would just work for any image that you use, because if you try to remove all the cultural traits from an image, you would still be, there was no way to detect whether someone is gay or straight. So it's a problem between correlation and causation. Okay, so with that, I'm already at the end of my talk. There's one very important thing. A machine learning model is only as good as the data it is fed. So most machine, or at least machine learning models, they are not just this one super intelligence that we can use and knows all the wisdom. It's basically just we feed in data and we get prediction based on the data we fed. So it's only as good as the data is fed. So with that, I would like to end my talk. As I said, my slides are behind that QR code. I do think we have time for questions, so I'm happy to take some questions. I'm also on LinkedIn, and I'm in this weird triangle between Mastodon, Blue Sky, and Twitter. Try to be active on all three of them. So if you want to connect, feel free to connect. And if you have questions, I will be there afterwards and also have time right now. Thank you very much.